All right, in our last example, we will figure out what happens when you add a salt mixture to a chemical tank. And really, the point of this is to illustrate the compartmental models that we discussed in the previous video. So welcome to this monster problem. So a tank contains 20 kilograms of salt dissolved in 4,000 liters of water, and then a water mixture containing 0.03 kilograms of liter per salt is entering the tank at the rate of 10 liters per minute and draining from the tank at the same rate. And the question is, how much salt remains in the tank after half an hour? So as usual, a picture says 1,000 words, so that is very useful in word problems. So you have this tank like this. And we know that in the tank comes a salt mixture of 0.03 kilograms per minute or per liter and 10 liters per minute. And out of the tank comes in some quantity, which we'll figure out, kilograms per liter, and it's draining out at 10 liters per minute. And the question is, how much salt is in there after half an hour? Okay, so of course, the first step is to name our variables. So always name your variables when you have a word problem. So QD, so not me, but the quantity of salt after T minutes. So QD is the amount of salt after T minutes. And it's in kilograms. So just as an example, and this will be important when we solve the differential equation, how much salt is there at the beginning? Well, the word problem tells us 20 kilograms. So Q of 0 is 20. And then, of course, we need to derive our differential equation. Step 2, ODE. And notice, I mean, that's very important in applied math, this constant interplay between real life and the math. So here we had a concrete word problem, and we translated this into math. And by solving the ODE, we'll translate it back to the real problem. So by this in and out equation that I discussed in the previous video, so the rate of change, so dq over dt, what this is, it's in minus out. So we need to figure out how much goes in minus how much goes out. Once we have that, then we have our differential equation. Now, let's see how much goes in. And for this, notice Q is in kilograms, so dq over dt is in kilograms per minute. So when you want the rate in, you want something in kilograms per minute. Rate in kilograms per minute. And again, the what rate in, so it's how much salt goes in. So the rate of salt going in, and what this is, since we want kilograms per minute, is just the concentration times the rate. So literally in the picture above, it's a 0.03 kilograms per liter times the rate of 10 liters per minute. So in this problem, really the units can help. So kilograms per liter, which is liter per minute, and that becomes, again, 0.03 kilograms per liter times 10 liters per minute, and that's really 0.3 kilograms per minute. So that's one part of the equation. For the rate out, it's just slightly more complicated. So it's still the concentration times the rate. So once again, kilograms per liter, and then rate, again, liters per minute. Now, the rate going out, again, based on this picture, it's still 10 liters per minute. Now, for the concentration, it's the concentration of salt in the tank. And more importantly, the more salt there is, the more goes out. So this quantity, this rate out, should depend on Q of T. And for this, you just use a formula from concentration, which is weight times over volume. So weight divided by volume. And that becomes, again, QT over 4,000. So not over 9,000, but over 4,000 times 10. And that's QD over 400 kilograms per minute. So therefore, what is our differential equation? So by in and out, we get a dq over dt. So rate going in, which was 0.3, minus rate going out, which is qd over 400. And so really our ODE becomes, so from q prime of t plus q of t over 400 equals 0.3. And we calculated the initial condition, which was 20. Now, as complicated as this looks, it's once again an integrating factor equation. Step 3. So solve the ODE. So integrating factor. Again, once again, the simple case of it. So e to the as 1 over 400t or t over 400. And this, you can see in the notes. And if you solve this differential equation, again, similarly to the falling ball problem, you find q of t equals 120 minus 100 e to the minus t over 400. Okay. And last but not least, we still need to answer the question, which is, how much salt is there after half an hour? I want to remind you, half an hour, that is 30 minutes, because our time is in minutes. So really, Q 30, that becomes 120 minus 100 e to the minus 30 over 400. That's roughly 27.22 kilograms. So in the beginning, we had 20 kilograms, but because of the amount of salt going in, it increases to 27.22. But the cool thing is also, by the way, so if you look in the long run, so if you want to see what happens as t goes to infinity, well, first of all, this exponential term goes to 0, because e of minus infinity is 0, and so q of t actually goes to 120 kilograms, which is precisely, interestingly, the volume of the tank, so 400 liters times the rate flowing in. So volume times rate in. And because I think things are balanced out as they are. And just one more thing I want to mention in terms of applications. So on the homework, there's a cool application on Newton's law of cooling. And also in the lecture notes, if you're interested, there's another population model example about bunnies versus foxes. And thank you very much.